So in this part of our lecture, we're going to be looking specifically at infrared and Raman spectroscopy. And this is probably what we go into the most detail on, and will take us a little bit longer than some of the other techniques. So in both of these techniques, infrared and Raman, again, they're attached very closely. And in both of them, we're hitting a molecule with energy, generally in the infrared or near infrared, and we're essentially looking at how it shakes. We're looking at vibrations of the molecule. And that's what we want. We want vibrational information. We have different types of vibrations. We have stretching and we have bending. And that's really the only types of vibrations you can have, is a bending or a stretching. We have different types of bending and different types of stretching, but they're all bending and stretching nonetheless. Sometimes we have things that are asymmetrical, and sometimes we have things that are symmetrical. And those lead to different features in our spectra. So for infrared, when we want something, or I should say, for something to be active in the infrared, it requires a change in the dipole moment in order for that mode to be active and to show in infrared spectrum. And again, the dipole moment needs to change. For Raman spectroscopy, it requires a change in the polarizability. In other words, how squishy is the electron cloud? Do we make it really dense? And if we make it really dense, that tends to be very low polarizability. And if we kind of make it really diffuse, then that tends to make it more polarizable. So what does that particular stretch or bend due to the polarizability tells us whether or not it's going to show up in a Raman spectrum. We'll look at other ways of determining that, so we don't have to necessarily look at the molecule itself and come up with a way to determine, is it squishy or isn't it. But we'll be able to use our character tables to help us out with this. So the connection to the symmetry, as I mentioned, the symmetric vibrations that we have. So we see symmetric vibrations here, symmetrical stretching. I think this would be considered an asymmetrical bend, or just a bend there. But symmetrical vibrations, such as the one we have in the middle, often change cloud size, but not the dipole. And so something like this second mode here, so that would make this mode Raman active, but it's not going to change the dipole because the H's are still in the same place relative to each other and to the oxygen. So the dipole itself really wouldn't be changing. So as I mentioned, we don't necessarily need to be able to look at a molecule, figure out all these different stretches and bends, and figure out if something is squishy or whatever. We can use our character tables that we learned in our last week's lesson to determine infrared and Raman activity. So anytime that we have an irreducible representation, or an irrep, that contains the X, Y, or the Z component, it is IR active. So as an example of that, we have the B1 in C2V. So here we have the B1, and we look over here and we see that we have this X. And so it is this particular operation here, this particular symmetry, is IR active in the X direction. We see also that we have the A1 active in the Z direction and the B2 mode active in the Y direction. Any irreducible representation that contains a quadratic is Raman active. Now, a quadratic is just something that is squared if you have two of the same axes or components, or if you have two different components multiplied by each other, that is also quadratic. So here we see that we have an X squared, a Y squared, and a Z squared, and so the A1 is Raman active, and here, as we mentioned in the bullet, the A2 is active because it's an XY, and that is also a quadratic factor, and so the A2 is also an active Raman mode. Some of the things we want to look at to determine if something is infrared or Raman active, or some of the ways that we can exclude things, is to use something that's called the mutual exclusion principle. And this deals specifically with molecules that have or don't have a center of inversion and how they differ from each other. So for molecules that have a center of inversion, so they have an I in their character table, no vibration can be both infrared and Raman active. So the term that we have, if something has a center of inversion, is we say that it's centrosymmetric. And so if we have a mode that has G or Gerada, then it is Raman active only and IR inactive. If we have something that is ungerade with a U in the description, then it is IR active only. And so as an example, CO2, SF6, and 2 all fall into the centrosymmetric list. They all have an inversion center. Just as an example of a character table that has a center of inversion, we have the I here, so just D2H. If we look at like an AG, we see that we have the quadratic functions in here, x squared, y squared, z squared, but we do not have an x, y, or a z in here. And so again, if it's gerade with a G, then it is Raman only, and then we see only quadratics, and so that indicates it's Raman only. If it is ungerade, we can come down here to the B1U, then we see that we have a Z, so it's Raman active, infrared active in the Z axis, but we have no Raman activity here. Now notice here we have the AU, and it is neither Raman nor infrared active, and that is possible too. The only thing this rule says is that it cannot be both. It does not say that it has to be either, and that's an important distinction. Now, if we have a molecule that is non-centrosymmetric, so in this case, the mutual exclusion principle does not apply, then modes can be both active. We can have a mode that is both Raman active and infrared active, or it can be neither active or just one of those active. And as an example, we have water. We use water a lot, and so C2V. And so notice here for like the A1 is active in the Z directions for IR, and also active in the X squared, Y squared, and Z squared directions for Raman. And down here we have X, and we have a ZX, we have a Y, and we have a YZ. Here for the A2, we have the XY, and so it is Raman active, but it is not IR active. So that is allowed as well. It can be just active in one, active in both, or active in none. So let's look at the math of how we determine all of these things. So what do we do with that? How many peaks do we expect for a molecule? And believe it or not, we can use character tables to tell us that. So we need to go all the way back to the molecule and the atoms and look at the degrees of freedom for motion of the atoms. And so for every molecule with n atoms, there are 3n degrees of freedom of motion. And these correspond to the x, y, and z directions. We do everything as a component of those. So the motions include translation, rotation, and vibration. And every atom in a molecule can translate in the x, y, and z directions. The molecule itself also has 3 rotational degrees of freedom, as it can rotate around the x, y, or z axes. And so if a molecule is linear, however, we discount the z-axis rotation, since the model, not the module, the model remains unchanged, or that should be molecule, not module. Molecule remains unchanged, and so we discount the z-axis rotation and put that back into the degrees of freedom. So where this ends up is that we have 3n total degrees of freedom. Your translation uses up 3 of them, moving in the x, y, and z directions. And your rotation uses up 3 of them for a nonlinear molecule and just 2 of them for a linear molecule. So all of the rest have to be vibrational modes, vibrational motions. And so we started with 3n, and we subtract 6 for the 3 in translation and 3 in rotation for nonlinear molecules. And the total vibrational modes for linear molecules are just 3n minus 5. And we'll see that this comes out when we do our math properly with our character tables. So for this little workshop here, we're going to use water because it's a nice simple molecule. It's easy to deal with. It has a very solid symmetry in our C2V without too many characters on there. So what we're going to look at initially is we're going to look at each individual atom and put its possible motion vectors on all those atoms. And so each atom has a possibility of moving in the x, y, and z direction for all of those. So we have 9 total vectors there. And if we look at our character table, and we're just going to look at each of these lines one at a time, so don't try to absorb this all at once. I just didn't have a way of showing each one of these lines one at a time. So in our first line here, we're going to look at our atoms staying. So we're just going to look at, do the atoms stay in place or not? And we're just going to count the number of atoms that stay in place when we perform a symmetry operation on them, on the molecule. So if we do an E, the identity operation on the molecule, well, all three atoms are going to remain in position, and so our character there is going to be a 3. When we do a C2, our character is only going to be 1, because this H becomes that H. Remember that our line of symmetry, our C2 axis, is going to go right through the oxygen. And so this H becomes this H, and this H goes around to that H, and so only the oxygen remains in place. And so our C2 character here is just going to be 1, and that's O for oxygen. For our sigma V in the XZ plane, and so we can look at our axes here, and our XZ plane comes out of the face of the screen there and goes across. And so when we do a mirror image there, again, our H's change place, our O remains the same, and so we run into the same character here with the 1 because the O remains in place. The two H's swap, and they're not counted in that case. Now, if we look at the YZ plane, so we have another mirror plane, so sigma V prime, and that's in the YZ plane. Our YZ plane is the plane of your screen, and so your molecule is also in the plane of the screen. And so the front half of one hydrogen just reflects to the back half of the same hydrogen, and same with the oxygens. And so all of those atoms remain in place, and so that also has a character of 3. Now, when we go down to our next step here, we're going to look at the contribution per atom, and we're going to look at the vectors here as far as how they change. We're going to look at the various vectors and see how they change, and it's per atom. And so we're only going to look at an oxygen or an atom that remains stationary for that operation, and then we're going to look at the change of the X, Y, and Z vectors total during that operation. And so for the E, okay, we're going to have 3, and so we can look at any one of these atoms. We'll just look at the oxygen because we're going to be looking at it a lot. And so for the oxygen, the Z axis remains the same. Z goes to Z. We can actually write these down. So we're going to have, let's start with X. So X turned into X, Y turns into Y, and Z turns into Z. And so we have a sum of 3 there, 1, 1, and 1. And so a contribution per atom there is 3. If we go to the C2, so remember what I said here with the C2s, we've got our C2 axis that runs down there, and so our H's move, and so we don't count our H's here, but the oxygen remains the same. So what we want to do is see what effect does the C2 axis have on the orientation of the different axes on that oxygen atom. Well, if we look here, our X goes 180 degrees around, so X becomes negative X, our Y becomes negative Y, and our Z remains the same at Z. And so if I were to make a table of this, I would have my trace would be -1, -1, 0. I'm sorry, not 0, 1. And if I add that up, I get a total character of -1. And so I have this -1 here for the C2. If we look at the sigma V, the XZ, again, my H's do not stay in place, and so we're not going to look at those. We're going to have the mirror plane in the XZ, and so that goes this way here. So if we look at how things change, we'll go to green this time. My X and Z vectors remain exactly the same. So X turns into X. Y, however, turns into -Y as it reflects through that mirror plane. -Y, not -X. just not a very well drawn Y there. And then my Z still remains the same, so my Z goes to Z. So really what I've got is I've got 1, -1, and 1. And if I add those up, I get +1. And that's exactly what we have right here. Now if we go to our next mirror plane, our sigma V prime, I've got a mirror in the plane here. Again, this affects all 3 atoms, but since the line just says contribution per atom, I can choose any of the atoms. They'll all be exactly the same. They have the exact same axes. They're reflecting through the exact same plane, so it wouldn't matter which one I choose. We'll just choose the oxygen again. And so if we look at our X, our Y, and our Z, so through that plane, the X is going to go this way and the -X. Our Y remains the same. So that plots as Y, and our Z remains the same also. And so I have a -1, 1, and a 1, and those add up to 1, and that's what I have here. So I have 3, -1, 1, and 1 contribution per atom. Now to get my gamma total, so this is the total effect here. All we're going to do is we're going to take these. Remember, these basically are matrices here. We're just going to multiply them down through, and it makes life really nice. I'm just going to take this top row and multiply it by the bottom row. So I have 3 times 3 is 9, 1 times -1 is -1, 1 times 1 is 1, 3 times 1 is 3. And what this does is it gives me my reducible representation of all the various motions of the atoms in oxygen. And that includes all translations, it includes all rotations, and it includes all vibrations. Now what we want to do is we want to create an irreducible representation to see what symmetry labels we can apply to all these various modes. And for that, what we're going to do is just apply our reduction formula. In the previous lecture, I called this a projection operator. This is not a projection operator. That was my mistake. This is a reduction formula. The projection operator is something quite a bit more complex. It's how you go from the results of your reduction and move it into your sulks. We didn't do that. So my apologies for the misuse of that term. Okay, so we're going to take all of our various coefficients here, just like we did in our previous lecture. So remember that for A1, we'll do first, we take the coefficient. We actually look here, it's so easy. We take the coefficient for each operation. We multiply it by our reducible representation number, and then we also multiply it by the character for that operation, for that symmetry. Okay, so for our first one, we're going to have 1 times 9. That comes from the 1, and the 9. Okay, if we carry on for A1, we're going to have our C2 next. So we have 1, 1, and -1. For sigma V and the XZ, we have 1, 1, 1, and then we have 1, 1, 3. If you sum those up, you get 12. 12 divided by 4 is 3. So we have 3 A1 symmetry modes. So we'll go to our next one, which is our A2. Just put it in different colors so you can see it differently. We end up with a total of 4 when we add all that up, and so that gives us a total of 1. For B1, we get 2, and for B2, we get 3. So if we sum this up, what we end up with is our total gamma, so our total motions here, our irreducible representation is 3A1 plus A2 plus 2B1 plus 3B2. Now, how can we get to where we want to be? If we look at our character table up here, we see that our translation modes, Z, X, and Y, so X, Y, and Z are in here. They account for, see, so translation, let's write this down, is A1 and, A1, B1, and B2. So I would have to subtract all those out. And then for rotation, we haven't really talked about rotation, but that's what these big R's are in our character table. These are the modes of rotation here. And so rotation has an A2, it has a B1, and it has a B2. And so for water, what we need to do is subtract all of those out, and we'll see where we end up with that. Okay, so this is what we talked about just a moment ago. We have our translations here, our X, Y, and Z, our rotations, Rx, Ry, and Rz. We saw in the table that our translations are A1, B1, and B2. A1, B1, B2. Our rotations are A2, B1, and B2. We subtract that out from our reducible representation, and what we end up with is 2A1 plus B2. Remember what we said, once you've removed the translations and the rotations from your reducible or from your irreducible representations, you remove the translations, you remove your rotations, what's left must be the vibrations. And so what we should have is 3 vibrational modes in water. That is exactly what the 3n minus 6 would tell us. We have 3 atoms in water, so 3 times 3 is 9. 9 minus 6 is 3. So we have 3 vibrational modes in water. Now, how do we assign those? So if we look here, we see that the Z matches for IR, and for the A1, we have it has a Z match for the IR, and it has quadratics for Raman. So the A1 is active for both IR and Raman. B2 down here matches for the Y for infrared and the YZ for Raman. So we want to know, is water Raman active? And we can say yes, it is, because it has symmetry elements that have Raman activity, and it transforms with quadratic basis functions. No peak is forbidden because there's no center of inversion, so we don't need to worry about that. We could ask, is it IR active? And we would also say yes, because we have IR activity in there as well. So for water, we would expect 3 IR peaks, and we would expect 3 Raman peaks as well. So let's take a look at actual spectra here. And so here's our water molecule here. Now it looks like we just have 2 peaks, a little sharp one there and a really broad one here. It turns out that this big broad one here is 2 peaks. We have 2 stretching vibrations that are very close in energy to each other. They overlap, and they only produce one peak in the spectrum. If we look at our Raman, we see some of the same thing, except you can see that they're a little bit farther apart, not a little better resolved here. So we have a peak right here. This other peak is probably right around here coming down, but it just adds on to it as it forcing that other one up. So there are actually 2 peaks there, again, very close together. And our third peak here is extremely weak down here. So we expected 3 peaks for both IR and Raman. We got 3 peaks, and we did that just through using the character tables and symmetry.